Okay, so now it's time to see what a real transistor differential amplifier would look like. So till now we have been dealing with this structure, right? And this current was going into some resistance, and let's say for this purpose of this discussion, I keep this resistance, the drain, some arbitrary resistance RD, right? And let's say this is V1, this is V2, this is Vx. So this is the small signal equivalent of the structure that we want. It's time to replace the small signal equivalent with its transistor level equivalent. So let's do that. So let's start with the GM on the left, that is GM1. So clearly it's a transistor. So we have to apply V1 here, but clearly we cannot apply simply V1, right? We have to apply V1 on top of some bias, and we know several ways of applying the bias, so I will not show them explicitly. I'll just assume we know how to apply the bias. Let's call this VB and this is V1. Okay, so this has to be Vx, this node has to be Vx. What do we need to do to the drain? In the circuit on the left, in the incremental model, the drain is shorted, right? So in this case, drain has to be higher voltage than shorted, which means that it has to be shorted to VDD. Okay. Now let's switch focus. If it for the same one, let's switch focus to the GM on the right. So this will be again another transistor whose other input will be incrementally V2, but again it has to be some voltage VB2. So let me call this VB1, let me call that VB2, and this is V2, and we have a resistance connected at its drain, and let's call this, and the other side of the drain is connected to VDD. Okay, and what should we do with the sources? As far as the two structures are concerned, the sources are shorted, so let's short them. Okay, however, if we short them, what's going to happen? Firstly, in a common source amplifier, the source is shorted to ground, right? But if we ground each of them, right, if we short them and ground each of them, will this work? This will not work because what is the reason? The reason is, in the incremental model, then this becomes a ground. If in the incremental model this becomes a ground, what is the this current will be GM1 times V1, this current will be GM2 times V2, and both of them will go to the ground. We are not going to get the difference of V1 minus V2, right? So why is the difference of V1 minus V2 getting generated? That difference was getting generated because Vx was a function of both V1 and V2, right? So if I go back, well, yeah, so you see Vx was like GM1 Vi plus GM2 Vf by GM1 plus GM2, right? So Vx in this case has to be GM1 V1 plus GM2 V2 by GM1 plus GM2. This is almost like a weighted average of V1 and V2, weighted with the value of its own GM, right? So, so clearly Vx equal to ground is not possible. But note that more importantly, what is there looking downwards from the source? It's an open circuit, right? It's an open circuit of resistance infinite. Okay, so which means that looking downwards from the source, I need to see an incremental open circuit. And what contraption do you know that gives you an incremental open circuit? You guessed it right. This is a current source, right? So let's put a current source and let's call this I0. Okay, so this is M1, this is M2, this is the voltage Vx, and this becomes the uh, transistor level schematic of our differential amplifier. Okay, so now it's time to investigate what are these voltages, what are the effects of this VB1, VB2, sizes of M1, M2, and so on. Correct? We have note that we have already done the incremental analysis before, because this structure came from the incremental analysis. Correct? So again, just to reiterate, what will be the current? What will be the current through this structure? Incremental current, assuming some current flows, assuming some quiescent current flows into M1 and M2. We don't know how much right now. So let's say the quiescent current here is I1, quiescent current here is I2, and of course I1 plus I2 has to be equal to I0, and this sets up some GM on M1 and some GM on M2. So what is the quiescent current through GM1? Not the quiescent current, I'm sorry. What is the incremental current through GM1? This is GM1 times V1 minus Vx. What is the current flowing into M2? Note that I have reversed the direction. So the incremental current flowing into M2 will be GM2 Vx minus V2, and then we equate these two and you will get what we got in the previous module, right? So now time has come to delve slightly deeper into this structure. So let's first figure out what is going to happen if uh, if the transistors M1 and M2 are not identical. Okay, so if transistors M1 and M2 are not identical, then what can you comment on the quiescent current I1 and quiescent current I2? So clearly the quiescent current I1 is half mu n Cox W over L of 1 VB1 minus Vx whole squared. Quiescent current of 2 will be half mu n Cox W by L2 VB2 minus Vx squared. Note that I have made an important distinction here, important assumption here, and that assumption is that both M1 and M2 are in saturation, right? So for M1 it's quite obvious. I mean, as long as we can keep VB1 to be one threshold voltage, I mean, as long as we can keep VB1, difference between VB1 and VDD to be less than one threshold voltage, then we are good. It's not particularly evident in case of M2. However, let's say the transistor M2 had gone into linear. What can I do? I can reduce the value of RD to increase the quiescent voltage at the drain of M2, and that would be good, right? So we are now mature enough to know what to do to get the transistor back into saturation if it has gone into linear. So I will make the assumption here to start off that our transistors are in saturation. Okay. So I will make another critical assumption. An assumption is since these two, I mean, this looks to be a symmetric circuit, right? I mean, as far as the operation of this circuit is concerned, or at least the physical nature of the circuit is concerned, it looks like there is nothing to distinguish if you apply an input to M1 or you apply an input to M2, right? The circuit will essentially behave identically, just that the directions of the incremental current will change, right? And that is why in general, even though in general you can choose any values, different values of VB1, VB2, W by L of M1 and M2 also need not be the same, but in most cases you will see that we tend to use same values of VB1 and VB2 and same values of W by L for M1 and M2, just because it gives us that symmetry in terms of I can choose which terminal to apply the input to without really thinking what's going to without really thinking of the effect of asymmetry. Okay, if we don't do that, what we need to do, we need to ensure that both the term the sizing of M1 and M2 is such that and the sizing of and the voltages of V1 and VB1 and VB2 are such that we have transistors biased in saturation. Okay, so to make the point, let me ask you, let's assume that this our transistors are biased in saturation and VB1 and VB2 are different, W by L of M1 and M2 are different. Can you tell me what's going to happen if I increase the volt? Let's say I don't have the incremental inputs. Let's say I don't have the incremental inputs. And let's say I increase VB1 from VB1 to plus delta V and VB2 to also VB2 to plus delta V. Now tell me what's going to happen. Will there be any what will happen to the quiescent currents I1 and I2? Any comment on what's going to happen on the quiescent current of I1 and I2? So see, the the most obvious way to think about this is to split this current source I0 into two sub current sources I1 and I2, right? So let's say I split this current source into two sub current sources, one having current of I1, the other having current of I2. Okay, okay. So if this were the case, right? If this were the case, can you comment on whether I will be having any current, any quiescent current through this wire connecting the two current sources? Note that these choices of I1 and I2 are not arbitrary, right? They have been chosen in such a way that the quiescent current, they will support the quiescent current of I1 and I2 through the transistors M1 and M2, right? So in other words, what is the current that is coming through this? This is I1. What is the current that is going out? That is also I1. What is the current coming through this? This is I2. What is the current going out? This is I2. Which means that for all practical purposes, I can say that this line does not exist, right? Because there was no current through this wire, right? So now tell me what's going to happen if I increase the gate voltages of M1 and M2, both of them by same amount delta V. So what is constant? Constant is the current sources I1 and I2. So they are not going to change, right? If they are not going to change, then what do you think is going to happen? If they are not going to change, then I may as well say that this current is not changing. So these currents will not change. These I1 and I2 will also not change, right? If they don't change, I have applied an increment of delta V at the gate. However, the current I1 remains fixed. Then what is the consequence? What is the only thing that can happen? The only thing that can happen is Vx of this terminal will also go up by delta V. This terminal will also go up by delta V, right? So regardless of whether these two terminals are connected or not, right, the sources of both M1 and M2 will go up by delta V in order to keep uh, your current constant. Okay, and I mean, note that we did this. I did this heuristic hand waving uh, analysis. We can also do it using brute force method, right? What we can simply do is, let's assume this delta V is a incremental input, right? It's an incremental change, right? We can also do, assuming that if delta V is small, within quotes small, right? What will be the change in I1? Or let's say if delta V is small, and you start off with the assumption that the currents I1 and I2 will change, right? If the currents I1 and I2, the quiescent current through M1 and M2 actually changes, which means that quiescent current through M1 has to increase and M2 has to decrease, or vice versa, right? It cannot be both, because I mean, where will that, if both currents increase, then which essentially means that the current source, since we have a current source at the connected at Vx, that will not allow for the increase of current on both M1 and M2, which means either the current through M1 has to increase or the current through M2 has to increase and the other has to decrease. So if we assume the current through M1 increases by delta I, right, this direction, which means the current through M2 will also decrease by delta I, which essentially means that the current is in the opposite direction of delta I, correct? So what is delta I? Delta I is the equivalent GM, which is the GM1 GM2 by GM1 plus GM2 times V1 minus V2. What is V1 minus V2? Delta V minus delta V, which is equal to 0, right? So which essentially means that if you apply an incremental input on both sides simultaneously in the same direction, right, there will not be any change in the quiescent currents, right? Another way of saying the same thing is that if we apply a common signal, if we apply a common increment to gates of M1 and M2, then there is no change in current. And in more technical terms, in using more jargon, what we call this is, this differential amplifier rejects common mode excitation, right? So this is a very critical property of crucial property of differential amplifier, which has immense use, right? So because now if uh, our differential amplifier is able to give us gain which is equivalent to the difference of two voltages, but is also insensitive to any common mode excitation, which means that I don't have to set VB1 and VB2 very accurately. VB1 and VB2 can be slightly different as well, right? And still our quiescent points won't get disturbed too much, correct? Okay, so another piece of jargon is so this is called often ACM, that is the ACM is equal to 0. So with ideal I naught at Vx, right? Often also Vx is also called the tail node, right? So Vx is also called Often Vx is also called the tail transistor, or the tail node in this case, tail node. Sometimes you will hear me talking about a tail transistor or tail node, which essentially means that anything that is connected to that node Vx. Okay, so at ACM is 0. What about if we apply a differential excitation? Let's say we apply, if V1, uh, if we apply Vi by 2, or let me say V1 equal to Vi by 2 and V2 equal to minus Vi by 2, right? Basically, I am increasing one side, I am increasing the gate voltage of M1 and reducing the gate voltage of M2. That's all I am doing. So what will be the incremental current? Delta I will be Gm times V1 minus V2, that is Gm times Vi. Where will this current flow? This current delta I is flowing into Rd, and it will create a voltage, right? So maybe I should draw this stuff again. Right? So where will this delta I flow? Note that even if I am sketching it using transistors, the analysis that I am doing is a small signal. By now we should be comfortable with without replacing the transistor with a small signal equivalent, and we will be able to visualize what the incremental model would look like even without replacing the transistor with its incremental equivalent, right? So if delta I is flowing upwards and it is flowing into Rd, what will be the incremental voltage at this node V0? The incremental voltage V0 will be delta I times Rd, which is Gm times Rd times Vi, which means the gain V0 over Vi is Gm times Rd. This is often called the differential gain, or AD, right? So this is called differential gain. Okay. Okay, so why is this split? Why do I bother about this differential gain and common mode gain? The reason we bother about differential gain and common mode gain is is because of the following reason. So let's say I apply an arbitrary input V1, arbitrary input V2 here, right? So note that I can express V1 as V1 plus V2 by 2 plus V1 minus V2 by 2, right? It's simple algebra, I broke it up. And also similarly, I can express V2 as V1 plus V2 by 2 plus, or rather minus, V1 minus V2 by 2, correct? So why is this useful? This is useful because in the context of differential amplifier, this is my common mode input, right? This is the common mode input, and this is the differential input. Okay, so since in the incremental sense our circuit is linear, we can use superposition, right? in the incremental sense, our circuit is linear, which means we can use superposition, which means we can, in principle, apply a common mode input here, that is, let me call this VICM, and let me call this VIDIF. So we can apply a signal VICM and VICM on both sides, and we can apply another signal VDIF plus VDIF and minus VDIF on both sides, right? We can do both simultaneously, or we can do both individually and do our analysis, right? So that is one of the reasons why you will see that breaking the input into common mode and differential mode often helps a lot. Okay. So let's stop here. In the next class, we will delve deep into some more detail into the properties of a differential amplifier. Note that we have till now neglected the effects of channel length modulation. We'll see what is the effect of channel length modulation. Again, we cannot assume we have an ideal current source all the time, right? So we have to see what are the non-ideal effects that come in if we use a real current source, right? Or by real current source, we essentially mean that a current source is essentially a transistor, right? So a transistor will have its own GDS or own RDS. So we will see what happens to this common mode gain, what happens to the differential gain, right? In the presence of these non-idealities. We'll also see how to size the transistors M1 and M2 in order to get certain quiescent gain and certain quiescent to get certain quiescent current through them, and so on, right? Okay, so let's stop here.